Hello and welcome to another video about similarity. Today we're going to talk about section 6.2, which is page 2 in our Unit 6 notes packet. Today we're going to talk about perimeter of objects. So first of all, I want to remind you that when we talk about perimeter, we have a specific definition for that word. Perimeter is going to be the distance around the outside of an object or figure or an image, whatever word you want to use. So when we think about perimeter, we're thinking about how much fence it might take to go around a garden or a yard. When we talk about area, we're thinking about how much grass might be inside that fence or that yard. But specifically, we're focusing on perimeter to start. So we're thinking about any object. If you know all of the lengths of the sides, we can add all of those side lengths together, and then that's going to give us the perimeter. So perimeter only uses addition. We should not be using any multiplication or division here until we're talking about doubling and tripling. So if we have an original triangle, let's imagine that we know all three sides have a side length of 1. That means you have 3 sides you add together. 1 plus 1 is 2, and then 2 plus 1 is 3. So if you're talking about a triangle where there are 3 sides and each one of them measures 1, the perimeter has to be 3. The question you're being asked today is about what if we scale that same triangle? So what if we double the triangle so that now instead of being a triangle where all 3 sides have a side length of 1, now all 3 sides have a side length of 2. So we've doubled the side length, and you'll notice that what happens is that 2 plus 2 is 4, plus 2 is 6. So when we doubled the triangle, we also doubled the perimeter, because if double means to multiply by 2, I got the side lengths by going from 1 times 2, and then the exact same thing happens with the perimeter. To go from 3 to 6, you would also double that or multiply by 2. So then triple would be if the triangle had 3 sides that all measured 3. This time we're adding together 3 plus 3, which is 6, and then we're adding plus 3, which is 9. So we tripled the original side lengths, and that means to multiply by 3. And what you'll notice is that that exact same ratio stays when we triple the perimeter of the shape. So it's interesting to look at 3 different shapes where the only thing that's changed is the measurement of the side lengths, but we have a direct proportional change with the perimeter of each of these objects. The ratio that exists originally from side length to side length is going to stay the exact same as the ratio of the perimeters of those objects. So if you know the relationship between the 2 side lengths, you also know the relationship between the perimeter. While this is interesting, it's also worth noting that that pattern should remain consistent throughout every shape where you compare perimeters of objects that have been scaled in some way. So if now we say, well, what if I have a square? Well, a square has 4 equal sides. So if you start out with this original square where there are 4 sides that each measure 1, if you add that together, you have 4 ones, which gives you a perimeter of 4. Now, if you double that square, you should kind of have an idea of what's going to happen. Without actually writing down all 4 of those side lengths, you should be able to think about how if I'm doubling the perimeter and I'm doubling the side length, that ratio stays the same. So if I take the original perimeter of the object and I multiply it by 2 to double it, then I have the new perimeter, which would be 8. 1 times 2 is 2. 4 times 2 is 8. Now the question is, what if I triple it? We would take the perimeter and you still multiply it by 3 because that's what triple means. The original perimeter was 4. So if I'm tripling the perimeter, the new perimeter should be 12. And this time I didn't have to do all of that addition. I can just use multiplication because I'm doubling and I'm tripling. Think about this as dilation, where you're just applying a scale factor. That's essentially what's happening here. So with a rectangle, we're going to do the exact same thing using our scale factors. But with a rectangle, we have two sides that are the same and two other sides that are the same. So imagine that we have the perimeter of a rectangle where the long sides are 2 and each of the shorter sides are 1. When I add 2 and 2, I get 4, plus 1 is going to give me 6. So what if I were to take that exact rectangle and double it? Well, now the long sides have a length of 4 and the shorter sides have a length of 2. So the exact same thing that's happening is that I'm going to continue to use this scale factor. If I have doubled the length of the sides, then I have to have doubled the perimeter of the shape because the ratios stay exactly the same. So if the original perimeter is 6 and I need to double that, 6 times 2 is 12, which makes sense. Next, I have to triple. I know that triple means to multiply by 3. So I have 2 times 3 means that each of those longer sides are 6, and 1 times 3 means that each of the longer sides are 3. So this time, if I triple the side lengths, I triple the perimeter, and 6 times 3 is 18. If you have the perimeter of one shape and you know the ratio of those side lengths, you can continue that ratio and you can actually find the perimeter that way. So if you know that you have an original perimeter, when I double and when I triple that shape, the perimeter is also doubled or tripled. So similar shapes have perimeters that are going to have the same ratios as their side lengths, which is a pretty cool feature. So let's think about if we know some information, but not all of the information in a set of shapes. If you're looking at these two triangles here, what you'll notice about them is that we have the perimeter of 2 of those shapes, and we have the side length of 1, and we're asked to find the side length of the other. So what we're going to do here is we're going to set up a proportion, and you can see that being written here in the margin. We're going to compare the 2 sides of one shape to the 2 perimeters of those shapes. So one fraction is going to be comparing each side length from one triangle to the next, and then the other fraction is going to be comparing the perimeters of those objects from one triangle to the next. So if you're thinking about the different parts of our shape, what you're looking at here are your 2 triangles, where the first piece of information you're given is about these 2 side lengths, where it's x and then 4. These are the sides, so this is going to be your first fraction. And it doesn't matter what order you write the fraction. You can write it as x over 4 or 4 over x. It doesn't matter, but I usually just work left to right, so that's going to be my guidance for you. If I'm writing a proportion, I need to look at the ratio that exists between the side lengths, so x over 4, and then the ratio that exists between the perimeters, which is going to be 9 over 12. Now, if you want to simplify the fraction, you're more than welcome to, but I just choose to go ahead and cross multiply from here. 12 times x is 12x, so numerator times denominator gives me 12 times x. The second numerator being multiplied by the denominator is going to be 9 times 4, and that gives me 36. After I multiply, I have to divide, so I do 36 divided by 12, and that gives me my x value, and 12x divided by 12 gets the x by itself. So let's make sure I match my color scheme here. Our x is red. 36 divided by 12 is going to give me 3, which means that x has to be 3. If you know the ratio of the perimeters, you know the ratio of the side lengths, and if you know the ratio of the side lengths, you know the ratio of the perimeters. So let's keep going. Here we've got a square. This time, the 2 side lengths that we're looking at are y and positive 2. If I'm going to write these as a fraction, I'm going to write y over 2. You could write it as 2 over y if you prefer. It doesn't really matter. The second part of this proportion then has to be the perimeters. So if I need to keep the same ratio, I need to know what that ratio is. You should have one complete fraction. 20 over 8 is going to be my complete fraction, so there's no variable there. When I go ahead and I cross multiply, I do 8 times y, which gives me 8 y's. Then, on the other side of the equal sign, I have to do the other set of cross multiplication. 20 being multiplied by 2, which is going to give you 40. Last but not least, we have to divide. So 8y divided by 8 is 1y by itself, and then 40 divided by 8 gives us 5. So since I knew the ratio of the perimeters, I can find the missing side length. And last but not least, we have our rectangle. In the rectangle here, the side lengths we have are a 5 and then an x. So the fraction I'm going to write is just going to go left to right, 5 over x. Pretty straightforward. Then the next side of my proportion is going to have the actual perimeters of these objects, making sure that they line up. So I wrote the fraction as 5 over x, which means that if I'm looking at these two perimeters, I have 12 and 36. If I want to make sure they stay in the same order, that fraction is going to be 12 over 36. Now, the next thing that I'm going to do is cross multiply. I would suggest a calculator here, but if you don't want to use a calculator, you're more than welcome to try to do this math longhand. 36 times 5 is 180. Then when we do our second set of cross multiplication, I have 12 being multiplied by x, which is just a little bit more straightforward. So what I can do to finish off my proportion is I can say that 180 is equal to 12 times x. Last step, still I have to divide. So I divide by 12, and then 180 divided by 12 is going to be 15, and 12 divided by 12 is going to be 1x. So I have successfully solved for x there using the ratio of the side lengths and the ratio of the perimeter working together. And there you have it. There's section 6.2. We have completed the notes. And if you have any questions, please let me know if there's anything I can do to help. Enjoy!